Hello everyone, fair disclaimer before we get into this. I am a horrible artist, so you'll have to excuse that. But what I want to do here is talk a little bit about Newton's third law and how it pertains to motion in a vacuum here. So I've got a couple things written already, or drawn already. First off, top left, that is Newton's second law. Force is equal to mass times acceleration. And that means that if we take a force and apply it to a mass, it is going to accelerate. Essentially, it's going to give that mass some motion up in the top right. Pressure is equal to force over an area. That'll come up a little bit later in the video. I also want to bring up Newton's first law, the law of inertia. That pretty much states that an object in motion remains in motion unless it's acted upon by an outside source. So, unless a force acts on an object, it's not going to change its motion. Up here, this fantastic artist rendering is the case of motion in a vacuum that I think most people do understand. It's kind of the case of the guy throwing the rock, right? You know, if you throw the rock this way, you're going to experience the same force in the opposite direction. So the rock goes this way, the guy goes this way. What I think people don't understand as well is the bottom case, and that's the case of air escaping from a balloon, in this case in a vacuum, and that will cause a motion in this direction, opposite direction that the gas is escaping. And a lot of people think that's not the case because this gas that's escaping has nothing to act on in a vacuum, and that's what we're going to be talking about in this video, because even though it doesn't act on anything, there's still going to be some motion there. Alright, now that we've wiped our slate clean, let's talk about the idealized case that we're going to be talking about. Instead of talking about something like a vacuum, what we're going to talk about is a box, an imaginary box that's got equal length sides on all four sides. So let's say these sides are all equal, and that the pressure is equal on each side of this box. Essentially meaning we've got a box filled with millions and millions of gas particles just bouncing around. They're hitting each other, and they're also hitting the box in pretty much every direction that you can imagine, right? The pressure is equal on all sides of this box. And since the area is equal, since it's a box of equal length on each side, that means the force is equal. So all of these exert an equal force on each side of the box. So we'll call that force F. We've got force F in this direction. We've got force F in this direction. So those two cancel each other out. We've got force F in this direction and in this direction, and those cancel each other out. So that means there's no net motion. There's no force applied, so there's no acceleration. Now what we're going to do, since seemingly we've got particles that are moving in every single direction in this box in a given time, is we're going to isolate just two of those particles. We're going to isolate a particle that's traveling this way and one that's traveling this way. Perfect opposites from each other. They're the exact same particle, so what they're going to do is create a force F here, exerting on this side of the box, and exert a force F on that side of the box. So we've got an equal force here and an equal force here. So that means there's no net force, which means there's no net acceleration, and therefore the box does not move. And of course, since nothing's interacting with the top of the bottom, there's no force there. Now this is where we're going to have to really start using our imagination, but the laws of physics that we laid out earlier, Newton's first and second law, are still going to be holding up. So we're going to imagine what we call time zero. Essentially an instantaneous moment with these same two particles. But now we say that this side of the box here has been eliminated. So what we get is this particle continues to travel as it would, and that's just going to continue out into the vacuum of space. So this particle is going to create no force. It's not going to interact with any side of this box, so no force is exerted. Now, when this box is opened up to the vacuum of space, this particle here has no way of knowing that. That particle does not have a brain. It does not know that this side of the box is open. It has no way of knowing that. And we just said, Newton's first law, the law of inertia, this particle is going to continue to travel as it was unless it's impacted by an outside force. And since there is no outside force, it's going to continue off and it's going to impact this wall. And it's going to create then a force F. And then the wall will then create a force F back on it, and that will eventually send this one also flying off into space. But what we've got here is no interaction on this side. So we've got zero force. And we've got a force F from this particle here interacting with this side of the box. So we've got a net force F on this side of the box, which means from Newton's first law, F equals ma. When we apply a force to a mass, we get an acceleration, and this box would then accelerate in that direction, regardless of this particle interacting with nothing, just going out into the vacuum of space. Because this particle is still traveling in that direction, it still keeps its momentum, it still keeps its inertia, it's still going to interact with that side of the box and create a force before it eventually will fly off into the vacuum of space.